तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
We have been talking about numerical integration of a function, and so in which we wrote the integral of a function f as I of f, and that is f of x dx between the limits a to b. We wrote this as approximation by saying that this can be approximated to integral a to b p k of x dx, and we said that the error in such integration is given by the next term in the polynomial, which is f x0 x k x integral a to b of this into psi k of x dx. So, that is what we have done so far, and then we said that in the case where psi k of x is a k plus 1th order polynomial, which is of this form, which is x minus x0 x minus x1 to x minus xk, and we will said that a particular case where integral psi k of x dx is equal to 0 is of interest to us, and then in that case I can use the difference divided difference method to write f of x0 x k x as, I can write that this quantity we can write this as f of x0 xk plus xk plus 1 f of x0 xk plus 1 comma x into xk plus 1 minus x. So, that was the important thing which we were going to use again in the coming discussion. That is the basic idea. Let me repeat this again, that the numerical integration is to represent is to carry out an integral of this form numerically when we cannot do that analytically. So, then we represent we approximate the function f of x, either the function f of x or the data points, tabulated data points we have, by a polynomial p k of x, and then do the integral of that polynomial. And if you do such an operation, then you have an error in the integration, which I represent by e here, which would be like the next term in the polynomial, that is the k plus 1th term in the polynomial, which can be written as that, the coefficient of the k plus 1 polynomial coming from the divided difference, and psi k of x, which is x minus x0 into x minus x1 up to x minus xk. Then there is a special case in which with the points x0, x1, xk are so chosen that we can write we have psi k of x dx in the limit a to b is equal to 0. In that case we can write this error term, okay, using this divided difference and substituting for this quantity here from this equation. and using the fact that this is a constant. Okay, so that constant multiplied by this using the property integral psi k of dx is equal to 0. So, leads to E as the error as integral a to b f of x0 xk plus 1 x minus xk plus 1 minus x into psi k of x dx. So, that is basically integral a to b f of x0 xk plus 1 comma x, that is a coefficient, and psi k plus 1 time of x dx. So, we see that now the error has gone into the k plus 2 order term in the polynomial. Okay. So, we have a polynomial approximation, the kth order polynomial approximation, but we had chosen x0 the points x0 to xk such that this was 0, and then the error would go into k plus 1th order in the polynomial. It is a k plus 2 term in the polynomial, not k plus 1 as it was here. So, the integral of the k plus 2 term in the polynomial. So, then the k plus 1 term which we have chosen here was also such that integral psi k plus 1 dx is equal to 0, and then so then we can use the same argument and then go to the k plus 2 term here, that is the k plus 3 term order term in the polynomial. So, and then by this method we can go all the way up to 2k plus 1 order in the polynomial, that we can by choosing x0 x1 xk xk plus 1 xk plus 2 etc. carefully, we can go all the way up to a term such that integral psi 2k plus 1 dx of x dx is equal to 0. Okay. In that case, our error would be of the order of the 2k plus 2 term in the polynomial. So, the integral of the 2k plus 2 term in the polynomial. We still have polynomial approximation by k terms, but the error would just go to 2k plus 2 term in the polynomial. So, that is the basic idea of the Gaussian rules which we want to discuss today. So, in the Gaussian rules, when you use Gaussian rules, we would write the integral of the function which we have been calling I of f as I of pk, where pk being the polynomial of order k, and we would write that as before. We have seen this in the Simpson's rule and midpoint rule, etc. That we would write that as a series of as a sum of a series of terms of this form, that is function value evaluated at x0, function value evaluated at x1, and function value evaluated at xk, etc. Okay. So, that is these. So, the idea would be to actually compute these coefficients a1, a2, ak, and then write it as a sum of this form. Okay. So, we need to evaluate these functions. We need to know the functions at this point x0, xk. So, now we can choose the points such that is what I just said. So, we have n points. We could choose these points such that our error is of the order of 2n plus 1th derivative of f of x, or we go into that term in the polynomial. So, the whole discussion of Gaussian rules is to find out how do we choose these points such that we have such a low error. So, that is a basic discussion which you would have today. So, the idea here is to write f of x dx as we said, I have split this function f into two product of two functions, that is g of x and w of x dx. So, this is now remember what we want to do is to choose the points x0, x1, x2, x0, xk such that we have psi 2k plus 1 dx is equal to 0. That is what we want to do, or in other words we want to write this as psi k of x, that is our original function here, x0 xk points, the product of x minus x0, x minus x1, x minus xk, and then we are going to choose x minus xk plus 1, x minus xk plus 2, all these points up to x minus x, sorry, xk plus 1 minus x, and xk plus 1 minus xk plus 2 minus x, etc., up to x 2k plus 1 minus x, and dx equal to 0. That is what we want to write. So that is a thing which we want to finally arrive at. Okay, so we have to have a method of choosing xk plus 1, k plus 2, k plus 2k plus 1, okay, such that we get this thing equal to 0. So we will have k plus 1 points here to begin with to determine the kth order polynomial, and then we need another k terms, okay, we have to choose another k points such that this integral is 0, so that our error is of the order of the k to k plus 2 term in the polynomial. Okay, so for that, first thing which we do is to write this function f of x, okay, as a product of two functions. So we will replace this function f of x as a product of two functions. So we are going to say f of x can be, or integral f of x dx a to b can be written as integral g of x into w of x dx between the limits a to b. So this has a double advantage. One is that it will give us, okay, this is required for us to find the points, that is one thing. Another thing is that, you know, this g of x, to approximate, see, we want to approximate this function f of x by a polynomial, but there may be problems because f of x itself may not be a well behaved function in the interval a to b. So in that case we could multiply it by, we could split it into g of x into w of x, where g of x is a well behaved function in the interval a to b. So we will have an advantage in this in that context here. So now it is a g of x we are going to represent by, we are going to approximate by a polynomial pk of x. Okay, so we are going to approximate g of x by pk of x of a kth order polynomial. That is what we are going to do. So we will write I of g is as an integral g of x w of x dx. Okay, so when you say I of f, we did not have the w, so just to distinguish from that, we write I of g when we say that it is g of x w of x dx. Okay, so now the form is, as I said, especially useful when we are able to split the function such that it is g is well behaved, and then we would approximate g of x by a polynomial, and then we would write g of x as pk of x plus the error in the polynomial, which is f x0 x1 xk x psi k of x. Okay, this being the product of x minus x0 up to x minus xk. Okay, so that is what we have, and then we can write now the error as this, right. So the error in this approximation would be this, instead of f, now we have g and a w here, right, psi k of x dx, where psi k is this product which we have just written down. Okay, so now we are choosing the points such that w of x psi k of x dx is equal to 0, right, that is what is required. So what we had done earlier in the case of midpoint or trapezoidal rule, we did not have the w, so always we were choosing is the point such that psi k of x dx is equal to 0, such that we can go to one order up, as I just explained here, right. Okay, but now our integral itself is g of x w of x dx. So if you want to go to higher order, okay, now error here is in this case is equal to integral a to b, right, g x0 xk x. Now there is a w there dx and then psi. That is what we have now as the error. Okay. So, now if you want to go to the k plus 1th order term, now the error in the k is in the k plus 1th order term. So, that is this is the k plus 1th order term. Now, if you want to go into a k plus 2 order term, what we need is integral a to b w of x psi k of x dx is equal to 0. Okay, that is what we would require now. We want this to be 0. So, w of x psi k of x dx is equal to 0. Then we will write this error as g x0 x k plus 1 x w of x psi k plus 1 x dx. If this is true, then we can write it like that. So, then we will go up and up to 2k plus 1 term. So, then the 2k plus 1 term we have to go all the way up to. So, from here we will continue and then write the error as integral a to b g x0 x k plus 1 x w of x psi k plus 1 of x dx equal to 0. And if this term the integral w of x psi k plus 1 of x dx is also 0, then we would go to higher term etc., till we reach the error as this as a to b g x 2k plus 1 comma x w of x psi 2k plus 1 of x dx is equal to 0. So, that is what we want to reach. Okay. So, that is what I have been summarizing here. Okay. So, let us go to the next level and then by choosing this to such that this is 0 and then we go to the next level and then so on and then till we reach the error to be 2k plus 1. Okay. So, now we will look at the method which gives us. So, now for a kth order polynomial, okay, so we have a polynomial of order k. Okay, so, we suppose we are able to choose these points k plus 1, k plus 2, k plus 3 to k plus m such that this is equal to 0. That is our aim, right. Okay. Then the error will become k plus m plus 1 dx. That is what I was trying to tell you here. So, we chosen k plus 1 term. Okay. So, another term here such that this is 0 and so we went to this and then we choose the next point etc. So, if you are able to choose m such points apart from x0 to xk, we choose another m points. So, we have two sets now. First we had x0 to xk which we use to construct the polynomial of order k, and then we have another m points which is xk plus 1 all the way to xk plus m. Okay. So, we choose we choose these points okay, such that integral g x0 xk plus m, we choose another point k plus m comma x, right, w of x into pi I going from 0 to now we have k plus m okay, into x minus xi, that product which is psi k plus m okay, dx equal to 0. Okay. So, if you are able to choose that, then the error will become of this order. Okay. So, I am repeating this again just to point out that what we want to construct. What we want to construct is the set of points. Okay. So, for which we use the orthogonality property of polynomials. So, what we want to do is we want to treat two sets of polynomials okay, and we use orthogonality property of polynomials okay, and construct these points. Okay. So, first let us choose this polynomial pk of x okay, and then we will construct we will be able to systematically construct these points okay, such that this is always true. Okay. So, we will write pk of x in the Legendre form. Okay. So, we will write pk of x in this particular form. So, we are having this approximation g of x by pk of x, and the pk of x we are going to write in the form we will not write it in the Newton form, okay, but instead we would write this pk of x in the Lagrange form, okay, that is sigma I going from 0 to k and pi j going from 0 to k, and j is not equal to I, right. So, we will write x minus xj divided by xi minus xj into g of xi. Okay, that is what we are going to write. Okay. So, this is our polynomial approximation. Okay. So, remember, so that is what we are going to use. Okay. So, in this construction our idea, our aim is to choose x0 to xk plus m, okay, such that this is 0. Okay. So, we will start with the polynomial approximation of the function g of x. G of x is given to us, and we will construct pk of x, the kth order polynomial first. Okay. And we will construct this polynomial kth in this using this Legendre form, which we have seen in the polynomial approximation interpolation scheme. So, we will write that as the product j going from 0 to k x minus xj by xi minus xj, obviously when j is not equal to I, okay, into g of xi. Okay. So, sum over all terms of I equal to I going from 0 to k. So, that is the, so now we have a sum of a series of terms, all of them of kth order, that is a polynomial pk of x. Okay. So, once we construct that, okay, the integrals of this are obviously given by this quantities, right. So, the integral Ipk of x is the integral of this. So, that can be written down in this form, that Ipk of x is given by the sum I going from 0 to k and the product j going from 0 to k x minus xj by x minus xk. So, now we have a w here and g of xi dx by definition of I. Okay, the integral is now defined with this weight w of x dx. That is our full function. Okay, so, now this can be, so that this can be written as ai g of xi. So, this integral I can write as ai g of xi, because g of xi is not a function of x. So, I can pull that out and then write it as sigma I going from 0 to k ai g of xi. You are going to write this integral I of p k as from this. Right. So, integral, so before we write the integral over x, so I can write g of xi outside. So, I can write g of xi, which is not a function of x, and then I would write integral a to b, right. Integral a to b sigma I going from 0 to k and pi j going from 0 to k, j not equal to I of x minus xi divided by xi minus xj. That is what you are going to write at the dx. Okay. So, now this quantity is what I call a of xi. So, it is g of xi, this is a of xi, this integral. So, it becomes g of xi. Okay, the sum also can be pulled out. So, it will be sum I going from 0 to, sorry, this is actually wrong, I should not write this here. Should sum I going from 0 to k g of xi integral a to b. Okay, so, g of xi into a of xi. So, a of xi is this integral. Right. So, that is what I am going to write. Okay. So, that's the form which we want to arrive at it. So, the whole purpose of this calculation would be to compute a of I. So, the two things, one is that we should be able to choose our points xi's, okay, such that we have error of the order 2k plus 1. We should be able to choose these points such that the error is of the order 2k plus 1 when we construct a polynomial of order k. Okay. And then we should be also able to compute a of xi. Okay. So, once we have that, okay, so now if we have this pair, that is xi A of xi pair, right. So, given that, then the polynomial, the integral of the function of this function, this integral, okay, just simply reduces to g of xi a of xi. So, if you know g of x and if you are given a set of points xi and its weights a of xi, okay, then I can write the integral as sigma I going from 0 to k g of xi a of xi. So, now note that a of xi is this quantity, this integral, right, and that does not have the function value anywhere. So, this method has this real advantage that if you are given a set of points x0 to xk, right, and then and the corresponding weights a of x0 to a of xk, which does not depend on the function value. So, given that you can integrate any function within the interval a to b. Okay, so, this quantity weights a of xi depends only on the limits, and this is a general polynomial here, okay, which does not depend on the function value g or f for that matter. So, I can just tabulate, if you give me this xi and a of xi, I can do any integral, okay, which is smooth and continuous, function or any integral of any function which is smooth and continuous, right, in that interval a to b. Of course, this will depend between the limit a to b, which a to b we use. So, that is the advantage. Okay. So, once you have tabulated this a of xi and a of xi, so that will depend on what order we choose, of course, because there is a product here, right. So, if you choose k or k plus 1 or k plus 2 order, okay, or k or m, whatever order you choose, the weights will differ, okay, because there is a product here. So, if you use a second order polynomial to do this, and there will be 2 values of x and 3 values of x and 3 values of that is x0, x1, k equal to 2 I mean. So, x0, x1 and x2 and a of x0, x1 and x2, and if you choose a fourth order polynomial, okay, that if you choose x0, x1, x2, x3, x4 and a of x0, x1, x2, x3, x4, and the first 3 values may not be the same, right? It will not be the same because there is a product here inside the integral. So, it will depend on 2 quantities, that it will depend on the limit and depend on the order of the polynomial which we are interested in. So, given that we get a set of xi's and a of xi's, and we still now learn how to do the compute the xi's, how to get the xi's, but given the xi's we can compute a of xi, and from that we can determine the integral I, right. So, that way it is already we see some advantage of using this Gaussian methods. Okay. So, the integral then reduces to a weighted sum of the function values, okay, and the weights ai and the points xi has to be given to you, or given the xi's we know now how to determine the ai's from this integral. Okay, so that's what the point is. Now again we are now reduced to only finding the values of xj's of this xi's. Once we know that, we know how to compute ai's, and given the order of the polynomial, and then we can construct the integral as a weighted sum of the function values at that points. Okay, so now we go down and then we will see how we construct that pointers. Okay, so once we have that, this quantity written in that form, then our error will now keep going down, right, k plus 1, k plus 2, k plus n, etc., up to 2k plus 1th derivative. Okay, so that is we have already seen. So, we have written now the error would be in this form, that is psi k, assuming that we can choose all these points, the error is psi k into x minus xk plus 1, x minus xk plus 2, x minus 2k plus 1, w of x dx equal to 0. That is what the error would be, that is our aim. Okay, so now since psi of x is this quantity, okay, we will write this as, now we have one polynomial here psi k of x, which is the polynomial of order k plus 1. This is of order k plus 1, and then we have another k plus 1 terms here, sorry, another k terms here. So, we have another polynomial of order pk of order k. Okay. So, the error which we are going to write will be in this form now. So, the final error, so assuming that we chose all the points starting from x0 to xk and then xk plus 1 to x2k plus 1, assuming that we can choose all this, our error would be, or we chose this point such that a to be, right, psi k, which we know is the product of x minus x0 to x minus xk, and then you have x minus x k plus 1, x minus x k plus 2 up to x minus x 2k plus 1 into w of x dx. That is the error which we have, okay, and that is what we are going to make it to 0. So, this is what we want to make, that is equal to 0, that is the a, right. So, now this is a k plus 1th order polynomial. Okay, so, we call that as p k plus 1, a polynomial of order k plus 1, okay, and then that we call as this as psi k of x. Okay, so, that is divided by some alpha, some quantity alpha k1, that is some number there, okay, just to give us the error to be done, okay, into alpha k1. We can choose it either way. So, we choose it as alpha k1. We just construct a polynomial, okay, alpha k plus 1 psi k. Okay, now this is of the order k plus 1 because this is a product of x minus x0, x minus x1 up to x minus xk, that is k plus 1 terms. So, this is one polynomial pk plus 1x. And then we have another polynomial, okay, which would be this one. Okay, now I call this polynomial, okay, I will call it q. So, that will be of the order k, right. So, there are k terms in this, so that will be of order k. Okay, so, we call it a qk polynomial. Okay, I construct a polynomial from that, which is x minus x to x minus xk plus 1 into x minus xk plus 2 all the way to x minus x 2k plus 1 divided by alpha k plus 1. We just construct this polynomial. So, this is a kth order polynomial, this is a k plus 1th order polynomial, and then I can write my error e, okay, such that it is integral a to b, right, it will be p k plus 1 q k w dx. Okay, so, that is the construction. So, there is a polynomial p k plus 1, there is a polynomial q k, and I write the error as integral a to b p k plus 1 q k w dx. So, that will be my polynomial, that will be my error now. Okay. So, I constructed two polynomials, one is p k plus 1 from this and the other is a q, in this case I written as q m. Okay. I can go all the way up to k, okay. M can go all the way go to k. So, that is 2k plus 1 terms. So, there are two terms. So, this is one polynomial and that is another polynomial coming from psi k. Okay. So, I can write the error as p k plus 1 q m in this case. So, in general q m. I do not have to choose k points here, I can just choose m points, then there will be an mth order polynomial and then this will be p k plus 1 q m w dx. I have chosen here k points. So, in general I can choose m points and then write this quantity as the error then as k q m. Okay. And then we have the orthogonality property of the polynomial. Okay. So, we have the orthogonality property of the polynomial which tells us that integral of integral. So, we have the what is called the inner product. So, which says that we can write a polynomial p k and q m, okay, and then we can always write this depending upon the limits, the weights. Okay. We have to choose the polynomial such it satisfies the limits and the weights. Dx is equal to 0 for all m less than k. That is the property which we are going to use. Okay. So, that is if you have a polynomial pk and another polynomial qm, okay, and then we can find w, okay, for a given limit a to b, we can find a w such that this quantity is 0 for all polynomial m which is of order less than k. Okay. So, that also comes from the fact that given a polynomial k or order k, I can write that as a sum of polynomials which are of order less than k. Okay, I can write it I can expand this polynomial as in terms of polynomials which are of order less than k, and that they form an orthogonal set. That is what basically this means. Okay, so I can write this in this form. Okay, so if I can choose my pk, okay, so that's the idea. So if I can choose my pk, okay, then I can also determine qm such that this is 0 from that quantity. So that's what we are going to use. So this orthogonality property is crucial in this analysis. So what we have done so far is to write the error in this term. Okay, in this case k. Okay, so it has to be k. I said m should be less than k here. Okay. So for this to be satisfied, this has to be m should be less than k. So I can go all if this is of the order k plus 1 polynomial, then I can go up to kth order polynomial here. Okay, that's what I'm trying to write here. Okay. So what I'm trying to say basically is that I can always find this function q k's given this polynomial pk plus 1. Okay. I can find the polynomial qk such that pk plus 1 into qk w dx equal to 0, okay, since k is less than k plus 1. So I can find this using the orthogonality property. So we choose error is this, okay, and then we write this as now this is a k plus 1th order polynomial and this is the kth order polynomial. In general, it's some mth order polynomial with m less than k, that's all. Okay, so k is the maximum order of this polynomial which we can write, and then we can write this as in this form. So that's the choice of this. Okay, now that's what we are using the orthogonality property. It's summarized here. Now remember, there's one more case where why this can always work is in this particular case. As I said that we can always find a p, a w and a for an a and b such that this is 0. Okay. And in this particular case, this will always work because the construction of p of k. So the way we construct p of k is important to make this satisfy or to make it satisfy this condition. We construct the p of k as by using tabulating the points. So, okay, so now we use this p of k and then we construct it in such a way that the points which you choose, that is x0, x1, x0, x1 up to xk, okay, are zeros, okay, zeros of pk of x. Okay, so that's what we are using. Okay, remember what we have construction of p, the polynomial pk plus 1x which we have constructed as pk plus 1 of x. We constructed that as sigma I going from 0 to k. So if it's k, it's k minus 1 here, and then pi j going from 0 to k, j not equal to I, x minus xi divided by xi minus xj into g of xi. Okay, so these points which you choose xi's are the zeros of this polynomial. Okay. So when these points x0, x0, xk are chosen as the zeros of this polynomial or zeros of this polynomial pk plus 1, because we are choosing k plus 1 points, that is 0 to k, that is k plus 1 points. So when these are chosen as the zeros of this polynomial, the xk points are chosen as zeros of this k plus 1 polynomial, okay, and then this qk, this function, will always satisfy this, okay, for any arbitrary values of xk plus 1, xk plus 2, 2k plus 1. Okay, so it does not matter. Okay, so the orthogonality theorem tells us that we can always find a polynomial of order m less than k for this equal to 0. Now it is left to us to construct this pk such that this is true. So now we construct the pk, okay, by choosing points which are the zeros of this polynomial, tabulating the function, okay, as the zeros of this polynomial. Sorry, we have to choose the points, okay, x0 to xk plus 1, and then those points we chosen by construction here as the zeros of this polynomial, because this is the way we construct this polynomial here. Okay. So once we have that polynomial constructed that way, that is we have tabulated x0 up to xk as the zeros of this polynomial, okay, then we have this quantity, that is pk plus 1 qk w of x dx equal to 0, okay, for arbitrary values of k plus 1, k plus 2 up to 2k plus 1. So I hope this is clear that there are 2 points. One is that we have the orthogonality property of the polynomials, okay, and from which this is what we are making use of here, and we are saying that we are tabulating x0 to xk, okay. We choose this x0 and xk as the zeros of this polynomial, that is by construction, and then we have this relation is always satisfied, okay, for arbitrary values of xk, xk plus 1, xk plus xk plus 1, xk plus 2 and 2k plus 1. So let me summarize this once again. Okay. So we have chosen these points as the zeros of the polynomial pk plus 1, right. Okay. Then the properties of the orthogonality polynomial tells us that the polynomials satisfy this relation for all values of m less than k for arbitrary values of x k plus 1 to x k plus m. Okay. It does not matter what is the points at which this q m is constructed, what are the points, what are the values of x at which this q is used to construct this q m. Okay. This is always true provided it is continuous there. Okay. So the choice of this polynomial is, okay, so of course this choice of this thing depends on the limits and the weight etc. that we already stated. So the assumption here is that I can always find this w for a given limit a to b, okay, such that this orthogonality property is valid, okay, and that's always true. Okay. So now given that we can construct now xk plus 1 to x2k plus 1 such that this is 0. So now we also want one more thing. Okay. So we wanted 2 things. One is that we want this to be 0 such that this is 0, right, this is same as that, and this is to be 0, and we also want that the next term, that when I add 2k plus 2 term, okay, and then this is of this is a 1 sign, right, this quantity is a 1 sign, so that I can I can say that my error is actually of the order of the k plus 2k plus 2 derivative of the function g, right. So for that we will choose this xk plus 1 to be x0, xk plus 2 to be x1 etc. So that this will become this pk plus 1 qk can be written as a square. Okay. So that is what we are going to do here. We just choose xk plus 1 to be x0, xk plus 2 to be x1 etc. such that the polynomials not only satisfy the orthogonality condition, also that we can write this quantity, that psi k into qm, that is this quantity pk plus 1 into qm as a square of the as a function, as a square, the product of the squares, and hence we will have one sign within this interval, and then we get the error in the polynomial as the integral to be the order of the 2k plus 2, the derivative of the function. Okay. So that's a summary of the quantity of that integral, and then we have some examples. Okay. So where we can use this quantity, the orthogonality relations are given here. Okay. So for example, if it's in the case of Legendre polynomials, okay, and this is the orthogonality relation. So note that the limits are from -1 to +1. Right. So in the Legendre polynomial, we are limited by saying that the limits has to be -1 to +1. Okay. And if you use instead of and then the weight is 0, the weight is 1, w is 1, while in the Chebyshev it's again -1 to +1, but the weight is 1 by 1 minus x squared to the power half. Okay. So if you have a function, this actually goes to, see, this goes to this diverges at x, this quantity, right, 1 by 1 minus x squared to the power half diverges at x equal to 1, these two limits. So, we may be having, if you have a function to integrate which diverges like that, you will have difficulty in integrating, but you can use this, and then this would be a well behaved function. Okay. And then there are other examples. For example, you could use like where then you have the weight as x to the power of alpha e to the power of minus x, and the limits are from 0 to infinity. So, depending upon what the limit is, okay, so if the limit is from minus 1 to plus 1, then you could use one of this, but if the limit is from 0 to infinity, then you could use this form to construct the weights, right. So, all this will go in the construction of the weights and choosing the values the values x0 to xk, because we want to choose those to be the zeros of the polynomial pk, our approximation pk, correct. So, that is what we want to choose. So, what the way we construct, so the way when you do the integral, we have to first choose the points at which the function has to be evaluated, and then calculate the weights. So, to calculate the weight, as we just saw, the weight will depend on the limit, right. So, the weight here, so the weight depends on the limit and also on the, so weight, these are the weights, right. So, the weight depends on the limits and also on the order of the polynomial, okay, and the values at which we have chosen the function to be, but it does not depend on the function value itself, okay. So, remember that. So, it does not depend on the function value, but we have to know the limits, and so what we see is that the orthogonality relation is coupled to the w function w and the limits, right. So, depending upon what limit we want to what are the limits of our integration is, we have to choose the corresponding method, either Legendre, Chebyshev, or Lagua or Hermite. Okay. So, this is also depends on what your functional form is. Okay. If the function has a 1 minus x squared to the power of half kind of singularity, then we use this, because then the function would be, your integral will be well behaved, we know that, and it will be easy to tabulate the function, because what we have to tabulate is g, not f. Okay. So, that will be well behaved. So, that tells us the choice. We will look at some examples of such quantities in the next class. Okay. So, and we want to, if you have the limits from 0 to infinity, if you want to do an integral to 0 to infinity, then you would use like okay, or minus infinity to plus infinity, then we would use Hermite. Okay. So, these are different examples of orthogonality relations which would be using, okay, to determine. Okay. So, the method is very simple finally. So, once we have decided what form of the what method we are going to use, whether we are going to use Legendre or we are going to use Hermite or whatever. So, one of these methods, then we will use the x0, x1 up to xk, and we have decided what order we want to integrate, or what order we want to what order of approximation we want to do, and then we would choose that many points as the first that many zeros of the polynomial p. Okay. So, if you are using the Legendre Gauss Legendre, and then we would say that, and we want to do a kth order Gauss Legendre, then we will choose x0 to xk as the first k zeros of the Legendre polynomial pk. Now, if you are choosing to be Hermite, and then we will choose this to be the first k zeros of the Hermite polynomial, and then we can construct the weights. So, we will construct the weights by just integrating this quantity. So, we will construct the weights a of xi as integral a to b. Now, the limits are fixed by what we are going to use there, okay, and that we will use just by j going from 0 to k, j not equal to I of x minus xi divided by xi minus xj, and whatever the w is, w of x dx, okay, that gives us the weight. So, this quantity and the limits and this xi's, okay, will be determined by whether we use Gauss, Legendre, Gauss Hermite, or Gauss Lagua. So, whatever the method we want to use, and that also be decided by the kind of function which you want to integrate and the limits. Right. So, the choice would be depending upon both the limits and the kind of function. For example, here in this case the limits are the same, but you can see that this has a weight as 1 minus x squared to the power half. Okay. So, that would be helpful in cases where the function itself has that kind of a singularity. If your function given to you was of this form, let us say f of x as some e to the power of x divided by 1 minus x squared to the power half, and then you are asked to compute I of f numerically, right, between the limits, let us say minus 1 to plus 1, and then you want to compute that quantity. So, a normal method would be difficult because if this limits this would diverge. So, but then you can write this as integral minus 1 to plus 1 g of x, which is now our e to the power of x, which is well behaved, and w of x dx. The w of x is 1 over 1 minus x square to the power half, and then we can use straight away this Chebyshev form, okay, right. So, that is the advantage of this method. So, let us look at one example here. Okay. So, that is to evaluate an integral of this form. Okay. So, now you see it has a limit 0 to 1 x squared e to the power of minus x dx. Okay. So, now we want to look at the 4-point, this is also called a quadrature scheme. So, there is a 4-point Gaussian method. So, we want to use 4 tabulated points, that is the polynomial will be of the order 3. Okay. So, we are going to 4 tabulated points is what we are going to use, x0 to x3. Okay. So, but the limits are 0 to 1, okay, and we have looked at this all the 4 methods which we know right now, they all have limits from minus 1 to plus 1 or 0 to infinity, minus infinity to plus infinity, etc. Okay. So, so what we have to do is to first convert the limits, we have to change the variables such that the limits goes from minus 1 to plus 1. Okay. So, that is first step to do, right. So, we will do that here. Okay. So, we will first take to make a slight change of variable, we say we will construct a new variable t, which is minus 1 plus 2x. So, we see that x goes to 0, when x equal to 0 t is minus 1, when x is 1 t is plus 1. So, the limits are now changed from minus 1 to plus 1 instead of 0 to 1. So, then we have the integral I, which is 0 to 1 x squared e to the power of minus 2x dx will now become in this changed variable form, right. I will substitute here, because 1 plus t whole square e to the power of minus 1 plus t dt. Okay. So, 2x will become 1 plus t, right. So, 2x is 1 plus t. So, minus 2x become 1 plus t. So, x square become 1 plus t whole square, and dt is 2 dx. So, there is a 1 by 2 extra coming in here. Okay, that is what we would get this here. Yes. Okay, and minus 1 to plus 1 is the limits. Now, we can use a standard form for Gauss Legendre. Okay. So, because now our function is this, okay, and limits are minus 1 to plus 1. So, I can use a Gauss Legendre form and write it in this form. So, now x0 and this form. So, these are the weights a0, a1, a2, a3, right, 4 points, and x0, x1, x2, x3 are the points at which I am going to evaluate this function. So, now what I mean by x0 is actually here, okay, this change variable scheme will be t0, t1, t2, t3, etc. So, now I want to evaluate this function. This is a function which I am going to evaluate, not this, right, because I have to make the limits minus 1 to plus 1, okay, and then I have to calculate the weights. So, now these points 0, 1, 2, 3 will be chosen as the first 4 zeros of the Legendre polynomial. Okay, that is what I would choose. Okay. So, now if you choose so the Legendre polynomial, the 4th order Legendre polynomial, which you have to use now, right. So, that will be this. Okay. So, we will choose the first 4 zeros of that Legendre polynomial. We need 4 points, we choose the first 4 zeros of the Legendre polynomial as the 4 points of that. Okay. And then the weights will be then given by this integral, correct. Okay. So, that is what you would be using. Okay. So, now it is in the changed form, change variable form. So, please pay attention to that. That is, we are in the changed limit form. So, we are going to use 1 plus t square e to the power of minus 1 by 1 plus t by 4. That is what our function is. Okay. That is what I am going to use as the function here, right. So, and then we are finding the we are going to evaluate this function at the first 4 zeros of the Legendre polynomial. Okay, now I've written the Legendre polynomial here. Normally these points these are always tabulated in many standard tables which list the zeros of this polynomial. So we don't have to spend time constructing that. And so we have this, we just read off the zeros from some tables, okay, and then we could construct the weights from this, okay, and in fact many of the weights are also listed in standard table of integrals and series. So only thing which you have to make sure here is that the limit is always -1 to +1. So we have to do the appropriate change of variable. Okay, so our x square e to the power of minus x square is now gone to 1 plus t square e to the power of minus 1 plus x, because we want to make the limit from 0 to 1 to -1 to +1. So that's a point. That's some point where you have to pay the attention to. Okay. So, but many times we don't want to do that. Okay, so we could write the program such that it is transparent in that sense. So we would just construct. We could just use this function itself. Okay, but then we have to evaluate now this function at 1 plus x0 by 2, 1 plus x1 by 2, 1 plus x2 by 2, etc. We couldn't evaluate earlier because we are evaluating this function. We could do it at x0, x1, x2, x3, but otherwise we have to do the change of variable and then evaluate the function. So that's also possible, but then the limit calculation would be from 0 to 1. Okay. So the weight calculation will be from 0 to 1. So, okay, so there are two different ways of doing it, but basic idea is that we are going to change the limits. Okay, so you could either change the limits and evaluate the integral. Okay, change the variable and evaluate the integral from -1 to +1 to calculate the weights, or you could change the tabulated points itself. Okay, the value of the tabulated points. Now x0, x1, x2 are the zeros of the Legendre polynomial, but you evaluate the function at 1 plus x0 by 2, 1 plus x1 by 2, 1 plus x2 by 2, etc. So that's the two different ways of doing that. Okay, so now so in general, if you have an integral, okay, so to summarize, in general, if you have an integral of this form, okay, f of x dx, and if you decide to use a Legendre form, okay, and then you could construct the weights by just doing this, that b minus a by 2, a to b, so choose the same a to b. We don't change the limits here, okay, but then evaluate the function at a plus b by 2. When you are evaluating the function, you change the variable there. Okay. So now these xj's are the zeros of the Legendre polynomial, but you are going to evaluate this function at xj prime, which is given by a plus b by 2 minus a minus b by 2. So pay attention to that again. Okay. So if you compute the weights, we don't change the limits, okay, but when you evaluate the function, we evaluate them at not at the zeros of the Legendre polynomial, but the zeros of the Legendre polynomial multiplied by this a minus b by 2 and subtracted from a plus b by 2, where a plus a and b are the limits of your integral, and as long as a and b are finite, we can do this change of variable and then calculate the integral. So we will see a computer code which implements such a thing in the next class.